Dmitrowicz, we've got like one of the most amazing things that's ever been discovered in the world, the periodic table in front. And it's got this weird shape, and it's because of these things we've been talking about, electron configurations. So, yeah, what say you?
Well, this diagram, we have it kind of behind from the last time we did the lecture. This right here is actually perfectly representing the periodic table, and it's actually really, really, really cool.
So folks, now what I want you to do is I want to get your periodic table out. So pause the video if you need to, get it out. All right, now that you have it out, let's take a look. Look at these numbers down here. 1, 2, 3, 4, 5, 6, 7. The 7 energy levels. Mr. Dmitrowicz?
This is pretty exciting here. 1, 2, 3, 4, 5, 6, 7. I'd also suggest this, if you have like a highlighter or anything, pull it out as well, because you're going to want to be able to highlight this out in just a second as well.
All right, so next thing we want to talk about is the 1s orbital. So hydrogen is 1s. I want you to write up at the top here, S1. All right. Hopefully they can see this is S2. Now we've got a little trick. Remember we've talked about the weird hydrogen helium thing. This is S2, okay? So 1s1. We read the table like a book, left to right, top to bottom. 1s2. Take a look here. This right here, and you want to put a box here, that these are the S's. So this is going to be, lithium would be 2s1, 2s2. All right, so the 2s, we talked about that, right, Mr. Dmitrowicz? 2s. The next orbital we fill is the 2p. Now,
how many are a set of P, by the way?
Huh?
How many are a set?
6. Now let's make a note. From boron to neon, 1, 2, 3, 4, 5. Check it out, 6. You see, this is your P blocks. Actually goes all the way over here. These are the P orbitals, all the way down here. If you will, we're going to draw a line from here to here. P's, there's 6 wide. These are 2 wides. These are your S's. Are you getting the idea? So let's read it like a book. 1s1, 1s2, 2s1, 2s2, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. Then we jump to what level after 2p6?
Now you're at the 3s.
So 3s1, 3s2. What happens after 3s?
You hit the 3p set.
We're just reading the periodic table like a book, left to right, top to bottom. Whoa! 3p1 aluminum, 3p2, 3, 4, 5, and 6. Next level, what do we do?
Goes from the 3p to the 4s.
New line, right? Next line when you were writing a book, 4s1, 4s2.
And here's where it's kind of cool, because here it goes from the 4s to the 3d. We didn't number this at the beginning, but we should have. The numbers right here, starting with scandium going down, it reads 3, 4, 5, 6. So if you see the numbers that are right there, he's going to rewrite them for you. So the main row starts at 4, and then it hits the D block, we call it the D, and goes to 3.
And it's no, D has how many? 5 boxes. 5 boxes, 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So scandium would be everything we said before. 1s2, 2s2, 2p6, etc. 3d1. 3d2, 3, 3d10. And then we get to the next level.
And again, now we see the 3d10 goes to 4p.
So gallium is 4p1. Again, the actual gallium would be 1s1, or 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1, 4p2, 3, 4, 5, 6. And then next?
Be 5. 5s.
Again, you just read the book, like the table like a book, left to right, top to bottom. 5s1, 5s2. But now that we sort of drop the level, if you will, we go to the D's. So this is a D, so it's 4d1. It's not 5, but 4d. 4d1, 4d10.
Now remind yourselves, when you hit the p's again, the numbers jump back up to what the regular row would be.
Yeah, now it's back to 5p1 and 5p6. So then we get to the 6th row, 6s1, 6s2. And then here's something interesting. It says LA to LU, and so you go LA to LU, this is now the F block, and we jump down here, and we go, and there are 14 of these, so this is actually 4F, actually lanthanum is, 4F1, 4F2, 4F14, then we jump back to 5D, 5D1 through 10, then we do
back to the
6P1 through 6, 7S1, 2, jump down here to the actinium series, etc. And these are going to be the 5Fs, and then we come to the 6D, and then the 6P. Now, let's show you a picture, by the way, of what the real periodic table looks like, because this, we always sort of pull these elements out, but what it really should look like is this. Notice in this diagram that what you've got is that the rare earth metals fit between the D's and the 6 and the 7 S's.
It's kind of like when you forget something and you put a little caret in, like you forget a word or a sentence when you're writing, and you put a caret in. The entire F block gets careted in between the 6S and the 5D, and as well from the 7S to the 6D.
So Mr. Dmitrowicz, why don't we, so let's now do iron. Let's find the electron configuration for iron. We're going to do first the box notation, but instead of using the table that we've been using before, we're just going to do the table, the periodic table. So we've got to spin 26 electrons, he's element number 26. 1s2, right? So we got the box notation that Mr. Dmitrowicz. Now our next level, right, is going to be the 2s2 level, or the 2s level, 2 electrons. Then we move over here to the 2p. See what Mr. Dmitrowicz is doing.
Even now, I'm putting one in at a time, even though I know I'm going to bypass them all.
And then we're going to go to 3s, this block. Reading like a book, left to right, top to bottom. 3p. 4s. And this is our last one because iron's last electrons in the 3D level, 3 and then D. Now notice that we have to fill in 6 electrons. So watch how Mr. Dmitrowicz writes these electrons.
So according to Hund's rule, we go 1 in each one. 1, 2, 3, 4, 5. And then we go back to the beginning and we put our 6th electron in. And that's what we end up with.
That's it. Now, there's a shortcut notation that we can do. So actually, let's write the electron configuration.
Well, yeah, we can write this, and the other thing you need to be aware of is that this right here is the last electron we placed, not this one right here. After we've done the orbital notation, we can write the electron configuration just by writing the number of electrons as superscript. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d, if we count up the number we have in here, it's going to be 3d6. Now even this, if you take a look at it, this is 26 electrons. Imagine if you'd asked me to do one that has 80 electrons. No one wants to do that. You want to do that?
Yeah.
No one wants to do that. So there's got to be a shorter way, and there's a shortcut using noble gases.
So the noble gases are super easy, right? They're the most stable atoms in the periodic table. They have their full shell octet. We've talked about this. They're full electrons. And if you notice, with the exception of helium, they end in P6. This is going to be 2p6, 3p6, 4p6, 5p6. And you might notice that if I do argon, for example, it's 1s2, 2s2, 2p6, 3, all that stuff we've got right there. So where does argon end? Where would argon end?
Well, what row is it in right now?
Well, he's in row 3, argon is, so he's going to be the 3p6.
So it's going to end everything up to 3p6.
So
right?
dot, 3p6. So we could just write, what do we write? How do we do this?
So watch, I could write argon, we always put in parentheses. I could write argon in place of all of this up to here. So instead of writing this, I could write argon because it replaces up to 3p6. Now in the past, if you didn't have a periodic table, you'd have to do some mathematics. You have to think, all right, we have to go up to 35 subtract, and figure out the math where you go. But with the periodic table, it becomes incredibly cool because what you can do is, let's put your finger on bromine if you would, where you were before. So what we can do is we can go to the nearest noble gas that we've passed. So if you go backwards, the nearest noble gas we passed has been argon. And so once we write argon down, we don't have to do any mathematics or anything. All we have to do is go, all right, cha-ching. Next row would be
4s2.
4s2. Now we're 3d.
Fill it all up, 10.
3d, 10.
And then 4p, 1, 2, 3, 4, 5.
4p5. Now this is not the example, this is for Fe, but I'm choosing right now Br, and we just randomly chose it because we did it before. This is a lot easier than writing all of this to get up to here.
I think we should do just one more, and just a crazy one. Let's do promethium, element number 61.
Woo! All right.
But we're going to do the shortcut notation. So we're going to back up, wah, wah, jump back to the 5th level, wah, wah, 6, back to the 5th level. It's xenon. you're gonna start with, right?
Mhm.
And all we have to do is build from xenon. And now we go xenon, remember, 6s1 and 2. And then we drop down to the 4. Remember, this is the 4 level. Make sure, by the way, on your periodic table that you write 4 and 5 right here, right next to these. 4f1, 2, 3, 4. That's it. 6s2, 4f4. After you put the old xenon, because xenon is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 3d10.
4p.
4p, 5p6. I did it wrong, but I was close. I'm trying to do
I mean, here's
fast.
an example. He's a trained professional, and
And I
even a
screwed
trained
it up.
professional, having to do that many, you run a risk of making mistakes. So how much easier is it to write XE 6s2 4f4 than that whole shenanigans we had to do before?
So folks, this isn't that hard. And again, what's the point of this? The point is we're trying to assign an address for all of the electrons because they're doing this jumping up and down 100 million times a second or whatever. It's huge, and it's what creates light, which we learned about. But where the electrons are, and honestly, what happens on the outside of electrons is what makes cool things happen. Like when we blew up the pumpkins, it's all about those electrons on the outside. It's all about the electrons on the outside, the valence electrons.
And what we're doing here, it should be noted, is we're putting everything in the ground state. So this is the lowest energy orbitals, and here's what's really cool about this. Can you put your finger on bromine again? So bromine has 35 electrons, right? So do you realize that the first 35 electrons of, let's say I have 100 electrons, do you realize the first 35 are gonna go in the same spot for every single atom? Like put your finger right next to it on argon. You know where it's first, oh sorry, not argon, xenon, is it? Krypton. Easy for me to say looking across the room. If you take a look at krypton, doesn't krypton have 36 electrons?
Yeah, so it's
The first 35 are going to go in the same spot that bromine has. So the number that we have assigned to each of these, we can do for anyone higher up as well.
So folks, now what you do is practice to write these things out, long notation and also shortcut notation.
See you next time.